Hi and welcome to Chemipedia chemistry classes for 11th and 12th standard. So in this video I'm going to discuss a simple trick to find out the nature of hybridization. Nature of hybridization present in a molecule. Okay, right. Now, so this is the first method. Okay. So there is a formula to find out hybridization. The formula is number of atoms attached to central atom. Number of atoms which is attached to central atom plus number of lone pairs of electron, number of lone pairs. So that to find out nature of hybridization, first you should know what is the central atom. What is the central atom in the molecule? That is one thing. And we have to see how many atoms are attached with that central atom. So that is the first term. Plus lone pair. You should know how many lone pairs of electron is there around central atom. Okay, once we know these two, we are able to find out the nature of hybridization present in the given molecule. Okay, to find out number of lone pairs, we are supposed to have the knowledge of valence electron, group number, etc. Okay, so if you want to find out the number of lone pair of electrons, just watch my previous videos. A simple trick to find out number of lone pairs electron. Okay, right. Now, so after adding these two things, if you get a number 2, which shows that molecule is having sp hybridization. Likewise, 3 na sp2, for 4 sp3, 5 sp3d, 6 sp3d2. If the number is about 7, sp3d3, 8 na sp3d4. Okay, right. Let us see some examples. Okay, right. So first example, a molecule CH4. Here the central atom is nothing but carbon. Okay, because it is located at the center of the geometry and it is surrounded by 4 hydrogens. Okay, right. Now the number of atoms which are attached with central atom is 4. 1, 2, 3, 4. Number of atoms attached with central atom 4, and number of lone pairs 0, because in methane the carbon has 4 valence electrons. In methane, the carbon has used all the 4 valence electrons, so that no more electron is left unused. So that methane there is no lone pair at all. So that lone pair, number of lone pair is about 0. About 4 plus 0, 4. So the hybridization is sp3. The number 4 hybridization is sp3 hybridization. Okay, methane has sp3 hybridization. Methane carbon undergoes sp3 hybridization. Okay, right. So next one, ammonia molecule. So ammonia NH3, and you know very well that in ammonia there is a lone pair or nitrogen atom. Okay, but here the number of lone pair is about 1. Okay, that you should know. Right. Now central atom nitrogen, it is surrounded by 3 hydrogens. Okay, but total number of atoms attached to central atom is about 3. The number of lone pair is about 1. But 3 plus 1, 4. If the total is 4, then hybridization is sp3, like previous one. Okay, right. Then the next example is water. Next example is water H2O, isn't it? Right, in H2O molecule, you know very well, in oxygen there are 2 lone pairs. Over oxygen atom there are 2 lone pairs, isn't it? Okay. With oxygen central atom, this is what actually the structure of water molecule, isn't it? So this is central atom. Then the atoms attached with central atom are 2 hydrogens. The number of atoms attached to central atom is about 2 hydrogen plus lone pair. Oxygen has 2 lone pair, 2 plus 2, 4. But even water also has sp3 hybridization. In water, oxygen follows sp3 type of hybridization. Okay, right. So let us go for the next example. Example number 4. So interhalogen compound IF7. Okay, right. So halogen has 7 valence electrons. Iodine has bonded with 7 fluorine atom. In the sense, iodine has used all its valence electron to make bond with fluorine atom, okay, which means it has no lone pair at all. Okay, right. But if you consider iodine as a central atom, it is surrounded by 7 fluorine. But number of atoms attached to the central atom is 7. Lone pair is 0. But total is 7. If the total is 7, the nature of hybridization is sp3d3. sp3d3. So look at the tabular column. totally 7. The hybridization is sp3d3. Okay, right. So next one, xenon tetrafluoride. Xenon tetrafluoride, isn't it? Okay. Actually, xenon has 8 valence electrons. It has used 4 to make bond with fluorine, so that 4 more electrons are left, which forms 2 lone pair. But this has 2 lone pairs, isn't it? Right. The central atom is surrounded by 4 atoms, 4 fluorine atoms, plus total number of lone pair 2. 4 plus 2, 6. 6 in the sense the hybridization is sp3d2. Okay, right. The next one, xenon trioxide, XeO3. XeO3, oxygen divalent. So which makes, each oxygen makes 2 bonds, isn't it? 3 oxygen, which means totally there are 6 bonds between xenon and oxygen, isn't it? Which means xenon has spent 6 electrons, remaining 2, which means it has 1 lone pair. First we have to find out the lone pair number, isn't it? Now oxygen is bonded with xenon, but the number of atom attached to central atom 3. 3 oxygen with xenon, isn't it? Lone pair 1. 3 plus 1, 4. So sp3 hybridization. Okay. The next one, a little bit complicated. XeOF4. XeOF4. Okay. Right. Central atom is xenon, which has 1 lone pair. Then atoms attached with central atom, 1 oxygen, 4 fluorine, totally this together 5, isn't it? Right. Number of atom attached to central atom 5 plus 1 lone pair 6. So hybridization sp3d2. Here actually 4 fluorine forms 4 single bonds, oxygen forms 2 bonds, up to 6 bonds, isn't it? Up 6 electrons are used, so 2 more electrons, 1 lone pair. Okay, 1 lone pair. The next 8th example, XeO2F2. XeO2F2, the number of atom attached with central atom 2 plus 2, 4, isn't it? Lone pair 1. Total number of atom attached to central atom 4. Lone pair 1. But total is 5. Hybridization sp3d. The next one, example number 9. Sulfate anion, SO4 2 minus anion. So far we saw neutral molecules. Here are some charged species. Sulfate anion, isn't it? Right. Here the central atom is sulfur, so which has 6 valence electrons, isn't it? Which has 6 valence electrons. The net charge is 2 minus, isn't it? So you have to add 2 more electrons with that. 6 plus 2, 8 electrons, isn't it? Sulfur, with sulfur, totally 8 electrons are available, isn't it? Right. Now, with sulfur there are 4 oxygen atoms, isn't it? So oxygen makes 2 bonds with sulfur. 4 oxygen, 8 bonds. Sulfur uses all the 8 electrons with oxygen atom. No more electron is left free. So that number of atoms which are attached with central atom 4 oxygen atom, no lone pair at all, because all the 8 electrons are used to make bond with oxygen. So total is 4. So SO4 2 minus also has sp3 hybridization. Okay, right. The next one, ammonium ion. Next one is ammonium ion, NH4 plus, isn't it? So here you have positive charge. So you have to subtract electron equal to the charge. Nitrogen, central atom, valence electron 5, total charge plus 1, so minus 1. For 5 minus 1, 4 electrons. So that in ammonium ion, over nitrogen, 4 electrons will be available. In ammonium ion, there are 4 hydrogen atoms, isn't it? Which means nitrogen use all the 4 electrons to make bond with hydrogen, so that no electron is left, not even a single electron is left unused, isn't it? So that number of lone pair is 0. Number of lone pair is 0. Then number of atoms attached with central atom. Total number of atoms attached with central atom. 4 hydrogen atoms, isn't it? 4. 4 plus 0, 4. So hybridization is sp3. Okay, right. The last one, hydronium ion, H2O plus. Here central atom oxygen, valence electron 6, but net charge plus 1, so you have to do minus 1. So 5 electrons, so that only 5 electrons are available with oxygen. Okay, right. Then central atom is surrounded by 3 other atoms. Number of atom attached to central atom 3 plus 1 lone pair, because totally 5 electrons are there. Among the 5, oxygen uses 3 electrons with hydrogen to make bond, isn't it? So 2 more electrons are left free. That forms 1 lone pair. This has 1 lone pair, isn't it? So total number of atoms attached with central atom 3 plus 1 lone pair, 3 plus 1 4. About hydronium ion also follows sp3 hybridization. Okay, so this is a very simple trick to find out nature of hybridization present in a molecule. Okay, even charge species also. Okay, I hope you understood how to do this hybridization calculation. Right, thank you. Keep watching my other videos.